Can you hear me?
Hello? Oh, hi. Yes.
You can share screen if you want.
Oh, okay, great. Is it visible?
Coming.
Can you see?
Now it's coming.
Okay, great.
Wait for a couple of minutes and then we can start.
Sure.
Sir, can we record your talk and live stream?
Yes, absolutely, yes.
Oh, okay. And also I will upload in YouTube also later.
Yeah, that sounds good.
Okay, sir. Thank you.
I'll just give it one more minute. Huh?
Sure. Yep.
Okay, good morning. Welcome to the morning session. Our first speaker will be Nikhil Srivastava from Berkeley, who will give an online talk. And if you want him to hear your questions, you have to speak into the mic. So the mics are there on each row. Okay, Nikhil, please.
Oh, well, thanks a lot. And thanks to the organizers for inviting me. I really was looking forward to coming in person, but unfortunately I couldn't make it. Okay, so this talk is called Many Nodal Domains in Random Regular Graphs. It's joint work with Shishendu Ganguly, Theo McKenzie, and Siddhant Mohanty, who are all from UC Berkeley. And please feel free to stop me if you have any questions at any point. So here's an outline of the talk. So I'll start by telling you the history of nodal domains and the motivation from some areas like spectral geometry and mathematical physics. And then I'll tell you what nodal domains of discrete graphs are and what's known about them, which is the subject of this talk. Then I'll state the new results that we prove. I'll give you essentially a full proof of a simple special case of the results. Then I'll sketch the general proof and I'll end with some open questions. Let's start with the history and motivation. So the basic example in the subject is given by a very simple ODE, namely looking at the Laplacian on an interval on the real line. So this is an operator on L2 of 0 to pi, let's say. And we can look at the Dirichlet eigenfunctions of the Laplacian. So that means functions that are in L2 would satisfy the eigenvector equation and satisfy Dirichlet boundary conditions, so there's 0 at the endpoint. And in this case, it's very easy to compute everything, and you can easily see that the spectrum is discrete. The eigenvalues are squares of integers, k squared, and the eigenvector corresponding to the eigenvalue k squared is sine of kx. So the first eigenfunction, second eigenfunction, and third eigenfunction are plotted here. And there's a particular structure that appears in this example, which is if you look at the zeros of the kth eigenfunction, then they partition the domain, this interval, into exactly k-connected components. So the first eigenfunction doesn't have any zeros. The second one has 1 0, and the third one has 2 zeros, and these partition the domain in general, the kth eigenfunction partitions the domain into k connected components. So this type of pattern persists if you look in higher dimensions. So in R2 you can look at a domain, a compact domain M in R2 with some smooth boundary, and then you can define the Dirichlet Laplacian on L2 of this domain. And this again is a positive operator, and it has a discrete spectrum because M is compact, and so we can label the eigenvalues lambda 1, lambda 2, and so on in non-decreasing order. And then we can choose eigenfunctions f sub k satisfying the eigenvector equation, where f sub k is the eigenfunction corresponding to the kth eigenvalue. So, okay, if there's multiplicity, there may be more than one choice of eigenfunctions, but let's just choose a sequence of such eigenfunctions and call that f sub k. So now we come to the key definition. So a nodal domain of an eigenfunction is simply a connected component of the domain minus the set of zeros of the eigenfunction. So for example, in this picture here, I've plotted the sixth eigenfunction of this rectangle. And it has zeros, which are indicated by these orange lines. And you can see that the zeros partition the domain into 6 connected components if you delete the zeros. And so these are called nodal domains. And the number of nodal domains of an eigenfunction will be denoted by capital N of f. And in this case, you can see that n of f6, the sixth eigenfunction, is equal to 6. And in general, this is the question we're most interested in. What is the relationship between the number of nodal domains of an eigenfunction and its index? That is, its numbering in the ordered sequence of eigenfunctions. Okay, so what's known about this? So there's a famous theorem of Courant who showed that in the setting of domains in R2, and it can be shown more generally for other manifolds as well, the number of nodal domains of the kth eigenfunction is always at most k. So this rectangle example is a sharp example for this theorem. And mostly in this talk, we'll be interested in the other question, which is, are there any lower bounds for the number of nodal domains? In which situations can we prove that there are indeed many nodal domains? So in general, there are no non-trivial lower bounds. In particular, Louis constructed a manifold which has an infinite sequence of eigenfunctions, but the number of nodal domains is just stays stuck at 2, even as the index of the eigenfunction goes to infinity. So you can have very high index eigenfunctions with only 2 nodal domains. So in general, there's no lower bound matching this upper bound. And so what people have mostly studied in this area is lower bounds, but now for specific classes of manifolds M in RD. So given some other additional structure of the manifold, can we prove a lower bound? And there are several results of this type. 2 of the highlights, so one is due to Jung and Zeldij from 2015. And what it shows is that for certain negatively curved manifolds, the number of nodal domains of the kth eigenfunction is at least Pauli log k. So this is going to infinity as k goes to infinity, though it's still less than the upper bound of k. And then another result is the result of Ghosh, Reznikov, and Sarnak, who showed that for certain arithmetic manifolds, so coming from number theory in some way, the number of nodal domains of the kth eigenfunction is at least square root k. Okay, so why do people care about this? So this is based on this kind of phenomenology of quantum chaos, which is an area that exists in mathematical physics, popularized by Berry and by Rudnick and Sarnak. And the basic phenomenology in this area is that if you have a classical description of a physical system in which the classical dynamics are chaotic, then this chaos should make some kind of appearance in the quantum mechanical description of the system. So in particular, if you have a manifold, which in this case corresponds to a phase space of some physical system, and it is classically chaotic, which is some property of the geodesic flow on the manifold, then it's believed that this should imply that now when you look at the eigenfunctions of the Laplacian on that manifold, they should also be chaotic in some sense, and specifically there should be a nice random model that describes them, so-called random waves. And this is a famous conjecture of Berry, that this should hold in some sort of great generality, this random wave property. So I'm not defining classically chaotic and random waves precisely. Instead, I'll just show you some pictures, which I stole from another talk. So in this picture, I have two domains in R2 on the left. So on the top, I have a circle, and on the bottom, I have a cardioid. And in each case, there's some kind of classical dynamics on this domain, which is a billiard, which means that a particle is moving in straight lines and gets reflected at the boundary by the law of equal angles. And you can see that this billiard looks very different in the circle and in the cardioid. So the cardioid is what's considered chaotic billiard, and this circle is not chaotic; it's integrable. So that's the leftmost picture, and the other pictures, the black and white pictures, are pictures of certain Laplacian eigenfunctions with index 100, 1000, 1500, and 2000. And you see that they also look very different. So the Laplacian eigenfunctions of the regular billiard are kind of periodic and have a predictable structure, but for the chaotic billiard, it looks like it's quite different and quite complicated. And various conjectures that this chaotic billiard, the structure is explained by a random wave model. Now, the other thing you'll notice is that if you look at the connected components of the zero sets in these two scenarios, they're quite different. There appear to be a lot more nodal domains in the chaotic case, although of course I haven't done a calculation. And this is indeed one of the predictions of Berry's conjecture. So Berry's conjecture is not known to be true, and it's considered difficult. But if you believe it to be true, it can be shown by Bogomolny and Schmidt, among other things, that it implies that the number of nodal domains goes to infinity as the index of the eigenfunction goes to infinity linearly in K. And so this is another reason why people are interested in proving these lower bounds on the number of nodal domains. Okay, so any questions about anything so far? Okay, so that was mostly just motivation. I'm not going to talk about manifolds in this talk. I'm going to talk about graphs. So let me now tell you what are nodal domains of discrete graphs. Okay, so the setup now is different. We're going to look at finite connected graphs G on n vertices. And given such a graph G, you can look at its adjacency matrix, which is an n by n symmetric matrix. And then you can also look at its discrete Laplacian matrix, which is just the diagonal matrix of degrees. I'll call that D minus the adjacency matrix. And this discrete Laplacian is again a positive semi-definite matrix. The bottom eigenvalue is 0. And if the graph is connected, the other eigenvalues are positive. They lie in this window between 0 and twice the maximum degree of vertices in the graph. And so again, this has you can order the eigenvalues in increasing order and define Fk to be the kth eigenvector, which is now just a vector in Rn. Okay, so in this talk, all the graphs are going to be regular. So actually, the matrix of degrees is just some constant D times the identity. So the Laplacian and the adjacency matrix will be used interchangeably. And in some cases, I will use the adjacency matrix. And the transformation is very simple. If lambda is an eigenvalue of the Laplacian, then D minus lambda is an eigenvalue of the adjacency matrix, but the order gets flipped around. So in this case of D regular graphs, the adjacency spectrum will be contained in the interval minus D to D. So that's the basic kind of spectral graph theory setup. And now we can define a nodal domain in kind of the same way, in an analogous way. So nodal domain, suppose you have an eigenfunction, an eigenvector of Fk of a Laplacian of a graph. A nodal domain of this eigenvector is a maximal connected component of the graph on which the eigenvector does not change sign. So it's a connected subset of the vertices on which either Fk is non-negative or non-positive. And another way of viewing this is you can take the graph and just delete all the edges where it does change sign. That's the analog of the 0 set. And then the nodal domains are the remaining connected component. So that's the definition of a nodal domain of a graph. And I'm going to denote the number of nodal domains of a eigenfunction Fk as n of Fk, same as I did before. So in this example, this is a tree, and this is some plotting of some eigenfunction of it. The green vertices are positive, the red vertices are negative, and so there are four nodal domains in this example. Okay, and so the question we're going to be interested in is a similar question. How is the number of nodal domains of an eigenfunction, of a Laplacian eigenfunction of a graph, related to the index of the eigenfunction. So for trees, so in this case, the nicest theorem is for trees. So Fiedler proved in 1975 that if you have a graph that's a tree, then actually the kth eigenfunction has exactly k nodal domains. This is always true. And this can be viewed as an analog of the simplest example of the interval that I showed you earlier, where the kth eigenfunction has exactly k nodal domains. And then there's a analog of Courant's theorem proved by Davies et al. In 2000, which says that for any graph G, if you look at the kth Laplacian eigenfunction, the number of nodal domains is at most k. And this is an exact analog of the Courant theorem. So there's this nice upper bound. And for lower bounds, as far as I know, there's only one general result that applies for a large family of graphs due to Burko-Lyko from 2008. And what he showed is that if you have a graph that has n-1 plus L edges, so that means the graph is nearly a tree if L is small, because a tree has n-1 edges. It's a connected graph. Then the number of nodal domains is of the kth eigenfunction is at least k minus L. So in particular, if L is a constant or something, then this is pretty close to k. So this is saying almost tree-like graphs have kind of almost tree-like behavior in terms of the nodal domains, and you can prove a lower bound like this. But this doesn't say anything for, let's say, a 3 regular graph, because then L is very big. So that's what's known for general graphs. And people have lately, in the last couple of decades, also been interested in what happens for random graphs. So there are 2 random graph models that have been considered. So the first one is random d-regular graphs, G and D, where D is a fixed constant, like 3 or 5 or something like that. And this was first considered by Kotos and Smilansky in this context in 1997, who proposed this as some kind of a discrete toy model of quantum chaos. So they had some kind of a heuristic belief that this should behave in some way like these so-called chaotic manifolds. And so you can ask the question, well, I generate a random d-regular graph, and I look at the Laplacian eigenfunctions. How many nodal domains are there? So they didn't prove any bounds at the time. But in this area, there was a very important conjecture of Elon in 2008, who made this discrete random wave conjecture, similar to Berry's conjecture. And the conjecture was that in this model of random d-regular graphs, the kth eigenfunction should also have some kind of a local random description. In particular, locally, it should look like a random eigenfunction of the infinite d-regular tree. So I'll define this precisely later in the talk, but basically it was a simple probabilistic model that's supposed to describe these eigenfunctions. But this was a conjecture. Elon did not prove this. It's still not known. But if you believe this, if this conjecture is true, then it indeed implies that the number of nodal domains of the kth eigenfunction is is order n when k is order n, for example. So yeah, if this conjecture is true, it implies that these eigenfunctions have lots of nodal domains. Another model, and there's experimental evidence for this conjecture by Elon himself and also by Decker, Lee, and Lineal in 2008. And they did some experiments. So luckily, this is a very easy thing to experiment with in MATLAB. And they obtained plots like this. So in this plot, the x-axis, so you generate a random d-regular graph on 1,000 vertices. The x-axis is the index of the eigenfunction, and the y-axis is the number of nodal domains. And you see that initially the number of nodal domains stays very low. So it doesn't start growing linearly all the way at the beginning, but after about 200, the 200th eigenfunction, it starts growing linearly. And so this experimentally seems to be true. Another model of graphs which was considered is Erdős-Renyi graphs, so where every edge appears independently with probability p. This was originally considered by Decker, Lee, and Lineal in 2008. And what they proved is that some kind of very different behavior appears for this model when the graph is dense. So if p is a constant, then they showed that the number of nodal domains of the kth eigenfunction is upper bounded by a constant depending on p with high probability for all of the eigenvectors. So for dense random graphs, they showed that the number of nodal domains actually is a constant. It's very different from what's expected for sparse d-regular graphs. And this was strengthened by Aurora and Bhaskar in 2011, who actually showed that if the probability is at least n to the minus 1 over 20, then the number of nodal domains is actually equal to 2 for all the eigenfunctions with high probability. So very different from what we expect in the manifold case. And then this was further sharpened by Huang and Rudelson, who showed that if P is at least n to the minus some constant, then not only are there two nodal domains, they have almost exactly the same size. So, the high level picture here is that in the case of sparse graphs, there's a conjectured behavior that predicts many nodal domains and kind of mirrors the behavior of these chaotic manifolds. In the case of dense random graphs, there's some kind of other behavior that is different from the behavior for manifolds, namely there appear to only be two nodal domains. Okay, so before I tell you our results, I mean, what's kind of the main, let me say a bit about the difficulties and the tools that are used to prove these kind of results. So I would say the main difficulty is that these nodal domains are very brittle objects. So if you have an eigenvector with some tiny entries and you flip some signs, then it can completely change the nodal domains. For example, it can connect to previously disconnected connected components or things like that. So nodal domains are a very sensitive object to tiny entries in the eigenvector. And the other thing is that the nodal domains really are defined in terms of one eigenvector. And most of the methods that we know in random matrix theory, they don't really say something directly about one eigenvector. They usually say something about, some kind of spectral window of eigenvectors or some kind of average behavior over a few eigenvectors. And in general, there aren't that many techniques that allow you to access entries of a single eigenvector directly. So these are the difficulties. And the way these difficulties are surmounted in the proofs, in the works that I mentioned earlier, are by proving results on eigenvector delocalization. So the main technical work that needs to be done to understand nodal domains is to prove results about delocalization of eigenvectors. And there are really two types of delocalization that are relevant. So the first one is to prove L infinity bounds on the eigenvectors. So to prove results like, the L infinity bound of the kth eigenvector is bounded by polylog n over square root n times the L2 norm. So this is saying that the entries are almost all the same size, right? Because if they're all the same size, you would get a 1 over square root n here. So this is called L infinity delocalization. This is carried out in the works of Erdős, Knowles, Yao, and Yin, and also in the work of Bauer, Schmidt, Huang, and Yao. And the second type of delocalization, which is distinct and incomparable from the first one, it's called no-gaps delocalization. This was introduced by Rudelson and Vrashinin. And no-gaps delocalization is a property that all of the L2 mass of the vector is not concentrated on a small set. So in particular, if you take any subset of the vertices that's linear in size, so it's some constant times n in size, then the L2 mass on that subset is at least some constant times the total L2 squared mass of the eigenvector. So saying that the L2 squared mass cannot be concentrated on a tiny set. So these roughly are the two kinds of ingredients that were used to prove the results on the previous slide, and we will use them in our talk as well. So that's what's known so far about nodal domains of random graphs. So any questions, comments about any of this before I move on? Okay. Okay. Okay, so let me now tell you what we proved. So here's the main theorem, and I'll parse it slowly. So let D be a number bigger, at least 3, and let alpha be a positive real number. And now let G be a random deregular graph. Then with probability approaching 1 as the number of vertices little n goes to infinity, every eigenfunction of the adjacency matrix of this graph in a particular spectral window, so I'll comment on this in a second. So the window is -2 squared d minus 1 to -2 squared d minus 2 minus alpha. So every eigenfunction corresponding to an eigenvalue in that window has at least n over polylog n singleton nodal domains. So in particular, I'll say what singleton is in a moment, but it's saying that every eigenfunction of an eigenvalue in this window has almost linear number of nodal domains. So linear is the highest you could hope for. This is saying it's at least n over polylog n. Okay, so let's parse these conditions a little bit. So what is a spectral window? Well, recall that Friedman showed that if you take a random d-regular graph, the spectrum is contained in the window -2 square root d minus 1 to 2 square d minus 1 plus some little of 1 with high probability. So that's where the spectrum lives. So in this cartoon here, I've drawn minus d and d. Those are the trivial bounds on the spectrum. Then I've drawn another interval, -2 square d minus 1 to 2 square d minus 1. This is where the spectrum lives with high probability according to Friedman's result. And then in yellow, I've highlighted this interval that's mentioned in the theorem. So this is an interval at the bottom end of the adjacency matrix spectrum. And it has some constant width depending on d. And so it's the bottom of the adjacency spectrum, so it's the top of the Laplacian spectrum. So the theorem is talking about eigenvectors in that window. And how many eigenvectors are there in that window? Well, by the Keston-McKay law, by proof of theorem of Keston-McKay, there are some linear number of eigenvalues in that window, where the constant depends on d. So it's not all of them, but it's some linear number of eigenvalues. Okay, so for all of those eigenfunctions, there are at least n over polylog n singleton nodal domains. So what's a singleton nodal domain? It's what it sounds like. It's a single vertex, which has a different sign from all of its neighbors. So that in the eigenfunction. So that means, well, it's a nodal domain of size 1, as shown in this cartoon. So that's the main theorem. Any questions or comments on the statement of the theorem?
What A sub Q is again?
Oh, sorry, that's A sub G. So that's the adjacency matrix of G. So G is a random d-regular graph, and A sub G is the adjacency matrix. Yeah. Okay. Okay. So in particular, this kind of proves up to the polylog factor the rightmost end of this picture from the experiment that I mentioned earlier. It shows that there's an almost linear number of nodal domains near the top of the Laplacian spectrum. Okay, so I'll start by telling you the proof of a special case of this theorem, namely the case of d equals 3, which is considerably easier. So this is a weaker theorem. So let's say d equals 3. Then what interval are we talking about? Well, sorry, it's actually not the special case. It's an even weaker theorem. I'm going to prove that when d equals 3, then if you look at any eigenvalue in the interval -3 to -2 minus alpha, so this is some other interval, then there are at least n over polylog n singleton nodal domains. And by Friedman's theorem, there will be some the spectrum is contained in -2 square root 2 to 2 square root 2, so there will be many eigenfunctions in this interval. So I'm going to prove this weaker theorem now. Okay. Let's prove this theorem. So this actually has quite a simple proof. So the proof rests on a very heavy delocalization result of Huang and Bauer-Schmidt, Huang and Yao, and the latest version by Huang and Yao, 2021, which is an L infinity delocalization result. And what it says is that suppose you have G, and that's a random 3 regular graph on n vertices. Then it's true that with high probability, every eigenvector of the adjacency matrix of this graph has an L infinity norm bounded by some log to the Cn over square root n times the L2 norm. So C is some universal constant. So this is an L infinity delocalization result. So this is the key input to this proof. So let's put this in our back pocket. So now the proof of the weaker theorem has a key claim, which contains the main mechanism of the proof, and this is the claim. The claim is, suppose you have this random 3 regular graph, and you look at an eigenfunction f, so AF equals lambda f, and lambda is a sufficiently negative eigenvalue, so it's less than -2 minus alpha. So suppose you have such an eigenfunction, and suppose you have a vertex x, which is not a singleton nodal domain. So it's not the case that all of its neighbors have their different sign. Then the conclusion is that this vertex X must have a neighbor Y in the graph such that the eigenvector puts significantly more mass on Y than on X. So f of Y is at least 1 plus alpha over 2 times f of X in absolute value. So this alpha is a parameter, I'm asking lambda to be sufficiently negative. This alpha is the parameter appearing in how negative I would like lambda to be. So lambda is at most -2 minus alpha. So the conceptual meaning of this claim is that if you have a non-isolated vertex X in the sense that it's not a singleton nodal domain, then this leads to some kind of exponential growth in the eigenvector entries. So then there's a neighbor that has significantly larger entry. Okay. Any questions about the statement of the claim before I tell you the quite simple proof of the claim? Okay, so let's see the proof of this. So the proof is quite straightforward. So let's say I have an eigenvector f, and let's say I have a vertex x in the graph that's not a singleton nodal domain. So in this cartoon here, I have a picture of x and its 3 neighbors y1, y2, and y3. Now the eigenvector equation, if I look at what it says on this vertex, it just says that lambda times f of x is equal to f of y1 plus f of y2 plus f of y3. Okay, so what do I know about x? Well, it's not a singleton nodal domain. So what that means is that there's some neighbor of x, let's say y1, in which f of y1 has the same sign as f of x. Let's say that sign is positive without loss of generality. So if f of x is positive, f of y1 is positive, and lambda I know is negative. Okay, so in this equation. So if something negative equals something positive plus some other stuff. Well, what that means is if I throw away this f of y1 term, so if I just delete this vertex y1, then I get an inequality. Namely, if I throw away that term, then the absolute value of the right-hand side has to go up because there's less cancellation. And in particular, I get this inequality that the absolute value of lambda times the absolute value of f of x is at most the sum of absolute values of the other 2 neighboring vertices, y2 and y3, whatever their sign is. Okay, so I delete this edge connecting x and y1, and I get this inequality. Okay, but now if I divide by 2, and then it's just saying that that the average magnitude of these 2 neighbors is at least lambda, absolute value of lambda divided by 2 times the absolute value of f of x, which by my choice of lambda is 1 plus alpha over 2 times f of x. So it's a very simple proof, and that completes the proof of the claim. So one of the neighbors by this, because I threw away y1, I average over the remaining neighbors. One of them has to be significantly bigger than f of x because there are only 2 neighbors. So I'm really using the degree 3 very heavily. This argument does not work for degree 4 and higher. Okay. So now, given this claim, it's quite easy to prove the theorem about many singleton nodal domains. How does the proof go? Well, I look at this eigenvector. So it's a random graph. I look at one of the eigenvectors, which is also random. It's L2 normalized. So there are many vertices x which have absolute value at least 1 over 2 square root n. And now, if x is a singleton nodal domain, I'm happy. If it's not, then by the claim, it has a neighbor which has significantly larger mass. So let's call that y1. And let's say its mass grows by a factor of 1 plus alpha over 2. Okay, now either that is a singleton nodal domain, in which case I'm done, or I just repeat the claim again. And that has another neighbor, y2, which has even higher mass. So I have this exponential growth of mass along a path, as long as I don't see a singleton nodal domain. But this is where delocalization comes in. So Huang and Yao says that the L infinity norm of the vector is bounded by polylog n over square root n. So this exponential growth can only go on for log n steps. And so after log n steps, this has to terminate, and I have to find a singleton nodal domain. And so now what I've proven is that for a large number of x, there's some singleton nodal domain within a neighborhood of radius log n, and that then implies that there are n over polylog n singleton nodal domains. So this exponential growth argument has some tension with the delocalization, and that's what gives us the nodal domains. So that's the proof of this weaker version of the theorem. Any questions or comments on this proof? Okay. So that's the weaker theorem. And I should say, okay, the same proof does work for higher degrees, but you get this weaker spectral window of -d to -d minus 1 minus alpha. So you can use it to prove that. The problem is that there are no eigenvalues in that window. So by Friedman's result, with high probability, there are no eigenvalues. So the theorem this proof just becomes vacuous when d is at least 5. So, okay, we have to do something else to prove the case for general d. And so I'll now sketch that. So the actual proof, what's the setup? I now have a random d regular graph where d is some number that's a constant. And I'm going to look at an eigenfunction f of that graph with eigenvalue lambda. So let f be that eigenfunction. And let's say lambda lies in this spectral window, -2 squared d minus 1 to -2 squared d minus 2 minus alpha. So again, the key issue is localization or delocalization. And the proof splits into two cases depending on the distribution of L2 mass of this eigenfunction. So the first case is the case when the L2 mass of f is not localized on a set of size delta n. So think of delta as being some fixed small constant. And in this case, it's not the case that 99% of the mass of the L2 squared mass of the function is on a set of size delta n. So this is kind of the cartoon here for this is shown on the left-hand side. That's some kind of that should be absolute value of f of I, but that's a histogram of the mass of the eigenvector on different vertices. And it's kind of, not all of it is not concentrated on a small set. In the second case is when this doesn't happen. The second case is that the L2 mass of this eigenfunction is localized on a set of size delta n for some subset S. That's a subset of the vertices. So then the histogram would look something like this. There's some subset S of the vertices, and almost all of the L2 squared mass is on that subset. In the physics literature, case 2 is called scarring, and case 1, I guess, is the absence of scarring, if that means anything to you. Okay, so let's now prove the theorem in each of these cases. Okay, so let's start with case 1. So case 1 is saying that the L2 mass is not localized on a set of size delta n. So that means if you have, for every subset S of size at most delta n, the L2 squared mass, I guess there should be a square, of the eigenvector on that set is bounded away from 1. Okay, so in this case, we can appeal to a beautiful result of Backhouse and Segedie from 2016, which is a proof of the discrete Berry conjecture, assuming this L2 delocalization, assuming this no gaps delocalization. So what this gives, so in case 1, we can, Backhouse and Segedie actually proves something like the discrete Berry conjecture. And what they prove is that with high probability, f looks locally like a random eigenvector of the infinite d-regular tree. Now, specifically, what does that mean? Well, it means the following. It means if I take my eigenvector and now I pick a random vertex x and look at its neighborhood. So that means that I have x and d other vertices. So I have d plus 1 vertices. And let's say I look at the restriction of the eigenvector on those d plus 1 vertices. That's a random vector with d plus 1 entries. Then what Backhouse and Segedie tells us is that the covariance matrix of this random vector, where the randomness is now over the choice of vertex, this is close to a very specific multivariate Gaussian with a very specific covariance matrix that's shown here. So the covariance matrix of this restriction of the eigenvector to a random neighborhood is a centered Gaussian with covariance matrix that has 1s on the diagonal and minus lambda over d on the entries corresponding to the edges incident to x, and some other stuff indicated by these yellow stars that doesn't matter everywhere else. Okay. So in the case when you don't have scarring, you have this nice Gaussian model for restrictions of the eigenvector at random vertex. Okay, so now the point is lambda is negative. So what this is saying is that the value of f at x is negatively correlated with the value at all of its neighbors. And okay, this is now something we can do a very explicit calculation with. And you just do some explicit calculation. It's kind of similar to, if you've seen proofs of semi-definite programming rounding in computer science, you just do some very explicit calculation. And just this negative correlation is enough to tell you that for this random vertex x with constant probability, it's going to be a singleton nodal domain. And that means that there are linearly many nodal domains. So this nice local random model just allows you to easily prove that there are many nodal domains. So this case is, in a sense, easy given the previous work of Backhouse and Szegedy. We don't have to do much extra. It kind of solves it for us. So that's case one, when the L2 mass is not localized on a small set. And this proof of Backhouse and Szegedy, I didn't say how the L2 localization comes in. The proof is based on a certain kind of graph limit argument, where a certain kind of weak convergence takes place. And to prove there's some tightness argument that in that which is necessary, and that's where you need this L2 delocalization. Otherwise, otherwise it could be that this result is true, except the covariance matrix you just get is a zero matrix, and then you don't get anything about the nodal domains. So that's case one. Any questions or comments on this? Okay, so I should mention that in case one, this spectral window did not really make an appearance. I didn't use this number -2 squared d -2 minus alpha, etc. I only used that the eigenvalue is negative to establish this negative correlation of this little Gaussian that I analyzed. Okay, so that's case one. And now we move to case two. So case two is a more interesting case. In this case, I have an eigenvector where the L2 mass is localized on a set of size delta n. So almost all the L2 mass on a small set. Okay, so in this case, I'm going to do something that's a bit more combinatorial. So here's a sequence of observations. So the first observation is, so let's say S is the subset on which this eigenvector is localized. By some kind of standard results in random graph theory, you can see that the induced subgraph on the small set looks like a tree. So in particular, it has very low average degree. The average degree of the induced subgraph on this small set S, I'm using that it's small, is very close to 2. It's at most 2 plus delta. So that's fact number one. So it's kind of indicated in this picture here. I've drawn the set S to be a tree with some, maybe a couple of more edges, these dashed edges. So that's a combinatorial fact about the graph. So we have the set on which the eigenvector is localized, and on that set, the graph kind of looks like a tree. Okay. The second thing I'm going to use is that because almost all of the L2 mass is on this set, the quadratic form of the eigenvector restricted to this set, which I'm going to call the energy, is similar to the quadratic form of the whole eigenvector. There's simply not much mass on the rest of the eigenvector, so I can just zero it out and it won't change the quadratic form very much. So in particular, I get this kind of approximate equality. So lambda is equal to the quadratic form of F with the matrix AG. So lambda is equal to F transpose AGF. But now when I pass to this induced subgraph S, because there was very little L2 mass outside, lambda is now approximately equal to the quadratic form of the induced subgraph on S. So let's keep track of this chain of inequalities on the left side of the screen. That's the first observation. Okay. The second observation is that if there are very few singleton nodal domains, so remember our goal is to prove that there are lots of them, right? So let's prove the contrapositive. If there are very few singleton nodal domains, let's say less than n over polylog n, then we can simply remove them from the set S, and that's not going to change the energy very much because of this L infinity delocalization bound of Huang and Yao. So the result of Huang and Yao says that none of the entries in the eigenvector are bigger than polylog n over square root n. So that means if I delete less than n over polylog n vertices from the set S, that's also not going to change the quadratic form with the adjacency matrix very much because each of those entries is small. So I'm going to delete those singleton nodal domains. And then I'm going to do some kind of pruning. I won't exactly tell you what it is, which is analogous to what I did in the D equals 3 proof, where I deleted this. Okay, so after I move the singleton nodal domains, there are no more singleton nodal domains, right? Now, if you recall in the D equals 3 proof, I used the fact that if a vertex is not a singleton nodal domain, I can cut the edge connecting it to one of its neighbors. So I'm going to do something similar here. I won't tell you exactly what it is. I'm going to refer to that as pruning the tree, or this approximate tree. And again, I can also do that while preserving the energy. And I can delete those edges again because they have the right sign. So in the second step, what I do is I delete the singleton nodal domains, and then from every vertex, I delete one incident edge. So this is the key property of the pruning. And I can do that while preserving the energy. And so at the end of this step, what I get is some edge subgraph of the induced subgraph on vertex set S, which I'm going to call a pruned tree. And the key property of this pruned tree, P, is that it now has maximum degree 1 less. It has maximum degree at most D minus 1. So this is analogous to the D equals 3 proof where I cut one edge incident to every vertex that's not a singleton nodal domain. So now I extend this chain of inequalities. Lambda is equal to the quadratic form of G, which is approximately equal to the quadratic form on this induced subgraph S, which is approximately equal to the quadratic form on this pruned subgraph P, the pruned tree, which now has maximum degree D minus 1. That's the key point. Okay, but now that's a contradiction because this pruned tree is, or approximate tree is also a tree-like graph with very low degree. And you can prove just using some kind of spectral graph theory argument that this pruned tree cannot have a large eigenvalue. So the spectral radius of this pruned tree is at most 2 times square root of the maximum degree minus 1 plus alpha, which is at most 2 times square root D minus 2 plus alpha. And this is now the implication I wanted. I just proved that if there are few singletons, then actually this eigenvalue lambda is bounded in absolute value by 2 squared D minus 2 plus alpha by passing to this pruned tree. But the contrapositive of that is what I wanted to show, right? So that's the proof of the general case, that if the mass is localized and there are few singleton nodal domains, then there's some version of this exponential growth argument that generates a contradiction by saying there's a subgraph whose spectral radius is too large. And that's where the 2 squared D minus 2 is used, because I have constructed this tree with degree 1 less. That was just a sketch of the proof, but any questions or comments on that sketch? Okay, so that's it. That's case 2, and now we've handled both cases, and that proves this theorem that for any D, if an alpha positive, if I take a randomly irregular graph, then with high probability every eigenfunction in this interval, and now we saw where the interval was used. It was used in this combinatorial argument with the pruned tree, has at least n over polylog n singleton nodal domains, and this polylog n that appears is the same polylog n that appears in the Huang and Yao delocalization result, because that's what we used to do the deleting of singleton nodal domains. And I should say that there's a complementary small observation. So the main theorem says that there are many tiny nodal domains. There are many nodal domains with one vertex. And there's actually an interesting complementary fact, which you can just prove using the expander mixing lemma, which says that also with high probability, the 2 largest nodal domains contain almost all the vertices in the case of large D. So the picture is kind of interesting. There are 2 nodal domains that contain most of the vertices, but there are also lots of tiny singleton nodal domains. And it would be interesting to know what the distribution of sizes of nodal domains in these graphs is. So that's it. That's a sketch of the proof. Let me end with a few open questions. So one, the obvious one is to improve the spectral window. So this 2 squared d minus 2 is obviously an artifact of the proof. It doesn't show up in experiments. And it should be possible to improve this for all bulk eigenvectors. And there's a natural route to doing this. The natural route is just to prove that the eigenvectors are always L2 delocalized. So you're always in case number 1. And case number 2 just never happens. And that's actually what we believe, that case 2 never happens. So that would be kind of the most definitive way to settle this problem. Just prove no gaps delocalization for random deregular graphs. So we don't know how to do that. We tried, but that's a natural open question. And then in the case of Erdős-Renyi graphs, there's still this kind of gray area for what happens for sparse Erdős-Renyi graphs. So for dense Erdős-Renyi graphs, we have a very clear picture. But you could ask, well, what happens around this threshold of log n over n, the connectedness threshold? This is a question asked by Eldon, Huang, and Rudelson. And is there some kind of transition as you decrease p from this kind of trivial behavior where you have like 2 nodal domains, or maybe not trivial, where you have this specific behavior where you have 2 nodal domains, to this different behavior where you have many nodal domains? Does that transition occur at some kind of critical probability? Another question is, can you say anything about the distribution of sizes or shapes of the nodal domain? So in this work, we focused on singleton nodal domains, which were very simple. And the reason we focused on them is that actually that there was a local way, there was a proof technique that kind of locally allowed us to say that they exist. But you could ask this for other sizes of nodal domains. And then most speculatively, going back to the original Kotos and Smilansky, I mean, does this stuff say anything about manifolds? Like, are these techniques at all transportable back to the setting of manifolds where we don't know things like this? So perhaps you could study random manifolds or something like that. Yeah, that's it. So any more questions?
We have time for a few questions. I was just curious, do you know results for eigenvalue nodal domains for G and kappa, where kappa is a graphon?
I don't. I don't actually. Yeah, that's another good question. Yeah, you could ask that question. I have not thought about that.
Okay, there are no further questions. We'll thank Nikhil again. So Nikhil, we'll go out for coffee. I guess you go to back bed, I guess.
Great. Well, thank you.